Picking up with this last example, example 3, we've realized that seeing the symmetry of this integral from -8 to 8, we must definitely test to see if we have an even or an odd function. Again, if it's odd, wonderful news, that integral immediately can be written as 0. If it's even, we're going to write what we've just written here, 2 times the integral from 0 to 8 of the integrand. Let's very quickly take this antiderivative. Bump 2/3 up by 1. Add 3/3 to it. We'd have s to the 5/3. But dividing by 5/3 is the same thing as multiplying by its reciprocal. From here, the antiderivative of 2 is just 2s. And we're going to evaluate this between 8 and 0. Hopefully you can see why working with 0 is so amazingly helpful. Look, I'll keep this 2 out in front. When we plug in the 8, we'll have 3/5 times 8 to the 5/3 plus 2 times 8. But wonderfully, when we plug in 0, I hope you can see that we're going to really just get a 0 all around. So wonderful news. That's why we love to be able to use this even property. Well, 8 to the 3/5, that's the cube root of 8, which is 2. And 2 to the 5th is 32. 32 times 3, well, I hope we know would be 96. So this is 96 all over 5. And here we have 16, but 16, if we got a common denominator of 5, that's 80 over 5. 96 plus 80, of course, is 176. And then don't forget we still have this little 2 out in front. When we multiply by the 2, we will get 352 all over 5. Okay, so as we continue on, let's take a look at part 1 of this fundamental theorem. Part 1, remember, dealt with the accumulation function. And here is the wonderful, wonderful corollary. We're seeing that if we took the derivative of this accumulation function with respect to x, we'll just get f of x. Wonderful, wonderful property here. I'm going to give you a little bit of a proof. And I think this is important for us to see. Let capital F of x be an antiderivative of little f of x. What that means is, another way of writing this, we can say, so the big capital F, when I take the derivative of that, I'll get little f of x. Well, if that's the case, let's just follow this through. We'd say d dx, we're going to take a derivative of this, c to x, and here's our f of t dt. Well, let's work this integral out with part 2 of the fundamental theorem. We'll keep our d dx out in front. We'll say take an antiderivative. Well, that's capital F. We have a dummy variable of t, though, and we'll plug in an x and plug in a c. Well, what is this exactly? Well, by that fundamental theorem part 2, we'll have capital F of x minus capital F of c. But this, of course, the capital F of c is just a constant, just some fixed number, because c down below is just some fixed number. Take the derivative of all this, and we'll have capital F prime of x minus 0. But look what we said up above. Capital F prime of x is really little f of x. So, there's your proof. We can see what I've highlighted is true. Lots of times kids will look at this and they'll say, oh, it kind of looks like the derivative is just canceling out the integral, and then you're going to be left with the integrand. In this regard, you could actually get away with that. We have to be very careful about that type of thinking, though. But according to this corollary, this theorem, what we're seeing is take the derivative of this accumulation function up here with x. What we will be left with is just plugging in an x into the integrand, and we are done. Wow, look at that. 1 over x plus 1. That's it. Well, what I'd really like to do, though, is talk about this other theorem. And this one we have to be especially careful about. You can see at the top of the page here I've written, this is an AP multiple choice question. They always put this on a couple of the BC exam questions in the multiple choice. Kind of like our last corollary, but more involved. What you want to see here is, yes, you do have a derivative d dx out in front, but wow, look at this. Your upper and lower bounds are both functions of x. We don't simply have an x up on top and some constant down below. Now we have two different functions. And look at this right here. According to this theorem, and I'm going to prove this also to hopefully help you see this, you can see very quickly this is f of g of x times g prime of x minus f of k of x times k prime of x. And very often what kids will notice and say is, wow, that kind of reminds me of the chain rule. And that's because this is the chain rule involved here, no doubt about it. Again, let's let capital F of x be an antiderivative of little f of x. And again, what does that really mean? I'm going to say i.e., that is, capital F prime of x is little f of x. Just like we had before. This proof, guys, is incredibly just like what we had before. We're following the exact same steps. We're going to take a derivative from g of x, well, from k of x to g of x. Here's our dummy variable of little f of t dt. And I'm going to take the antiderivative. Let's keep our d dx out in front. But I'd like to take the antiderivative of little f. And like I said, we're going to get big F. And the fundamental theorem, part 2, says you take your antiderivative and then you're going to plug in your top bound minus your lower bound. Now, look what's about to happen. You could say, well, this is capital F of g of x. If you thought the chain rule was coming up, you better believe it is. Hopefully you can see where we're going. G of x and k of x are both functions of x. They are varying. They're not necessarily constants at all. So what's really happening? Take our derivatives. Chain rule. F prime of g of x. Take the derivative of the inside. Here's your g prime of x. Minus f prime of k of x. Multiply that times k prime of x. How do we finish this proof? Well, very quickly, notice what we were saying up above. If capital F of x is really an antiderivative, that means when I take the derivative of capital F, I'm back at little f. Well, here's capital F prime. That's really little f of g of x times g prime of x minus little f of k of x times k prime of x. Wow. I hope you can see what's happening. Let's revisit this. Plug in your upper bound into your function and then multiply by the derivative of that upper function, g prime. Then subtract, plug in the lower bound into your integrand, and then multiply by k prime of x. How would that look? Well, let's do a quick problem. For number 5, d dx, what that means is plug in x cubed into the integrand. The dummy variable is a t, so wherever I see a t, I'm going to plug in x cubed. So I'll have x cubed, and then I've got that cubed, plus 1 raised to the 10th. I'm substituting x cubed into the integrand, but then I've got to multiply by the derivative of that upper bound. The derivative of x cubed is 3x squared. Then what? Then I'll say minus, plug in your 3x, you'll have 3x cubed plus 1 raised to the 10th. But now take the derivative of your 3x and you'll get 3. Let's clean it up. X cubed cubed, you get x to the 9th plus 1 raised to the 10th. I'm going to bring my 3x squared out in front. Let's see, inside here, 3 to the 3rd is 27. So I'm going to get 27 x to the 3rd plus 1. Raise that up to the 10th, and then just bring a 3 out in front. So that's how you do a problem like that. A little bit complicated, but we just need to keep getting some practice on it. Look, for example 6, we're going to do the same thing. Again, look for your dummy variable. Here's a t. That's acting as our variable inside the integrand. What am I going to substitute in for a t? Well, I'm going to plug in x to the 4th. So I've got, instead of seeing t to the 3rd, I've got x to the 4th to the 3rd plus 2. Well, then what? Now I've got to take the derivative of x to the 4th. That's 4x squared. Now I'll say minus. Now I'm going to plug 2x in. So I have the square root of, well, now I'll have 2x cubed plus 2. Almost done. Now you got to take the derivative of 2x, and you just get a 2 itself. Well, inside here you'd have x to the 12th plus 2, and then you'd have your 4x squared out in front. Inside this other radical, 2 to the 3rd is 8. Here's 8x cubed plus 2, and then you bring a 2 out in front. All right. So, as we're taking a look at our last accumulation function, you could be given a graph of f. And an accumulation function, g of x, is the integral from 0 to x. Let's see, for part A, could we find g of 0? Substitute this in. Look at this, 0 to 0 of f of t dt. We don't even need this graph to see. When I plug in a 0 for x everywhere, 0 to 0 we saw yesterday, that's just going to be a 0. Look, when I plug in a 1, I'll get from 0 to 1 of f of t dt. Well, I'm saying find the net area from 0 to 1. Well, from 0 to 1, guys, take a look at this. This is a triangle. This is a triangle. And we could find geometrically that we've got 1/2, a base of 1. My height is actually a 2. Look, the 2's cancel out. You're just left with a 1. Finally, what if we found g of 2? Well, that, letting x equal 2, we're going to integrate from 0 to 2 of f of t dt. Finding this geometrically, this time we're just going to go out a little bit further, and we're going to say, now I want this net area, and of course it's just regular area, isn't it? Going all the way up to here, it's that triangle plus the rectangle. It's the triangle plus the rectangle. So my goodness, we already found that the triangle had an area of 1. Look, from 2 to 1, this base of the rectangle would be 1. You could see the height would still be a 2. So this is 1 times 2 is a 2. And we saw that the area of the triangle was a 1. So we'd say 1 plus 2 would equal 3. So this is how we could look at this accumulation function. G of x is a function that you could think of as being the net area from from 0 up to a given x value. And we're going to talk a lot more about accumulation functions Keep working at this. Best of luck.